This is the fourth video, excuse me, in the review for the midterm. This covers Unit 4, which is bonding and nomenclature. To start with, let's talk about ions. Valence electrons are going to be the electrons on the outermost orbital of your atom. Okay, and these are the ones that are involved in chemical bonds. A cation is any positively charged ion, and to become a cation, you will lose one or more of the valence electrons, and everything wants to be like your noble gases. So this is the noble gas column, and everything wants to be like it. An anion is going to be a negatively charged ion, and it will gain electrons to get a noble gas configuration. And so if you look at this chart here, your transition metals are going to have variable charges. They're going to depend on what the particular element is and what the compound is, but generally group 1 is +1, group 2 is +2. If we skip to group 13, it becomes +3. Group 14 is odd because it can be +4 or -4. Group 15 then switches over to -3. 16 is -2. 17 is -1, and 18 is 0. They don't have a charge. A couple of the other ones that are pretty constant, zinc is always +2, silver is always +1. Tin and lead both can be +2 or +4, so they are treated like transition metals when we come to naming them. So these are charges, these charges you should know and should have written on your periodic table. Now, once you create these ions, you can create an ionic bond. And the ionic bond is just the electrostatic force that holds these positive and negative electrons, ions together. And an ionic compound is something that contains an ionic bond. And these particular compounds have a very specific set of properties. One, they often form a crystal lattice due to the electrostatic attraction. They have a high melting point and boiling point, which depends on the strength of the bond. And they're able to conduct electricity well. Solids, they don't conduct electricity, but if you dissolve these solids in water or other solutions or other liquids, then they have a huge conductivity. Now we can take the cations and anions and we can make a formula. So the formula for an ionic compound will typically have a cation, which will be first. It will typically be a metal, so it will be from the left side of the periodic table. So remember, metals are on the left side. It will also have an anion, which will be negative. So this is positive, this is negative, and this is first, and this is second. The anion is always second. And it's typically a non-metal, okay? So it's going to be from the right side of the periodic table. Okay. We have a couple different types of ions we have, or two different types. We have the monatomic ion, which is one atom, and transition metals, remember I was talking about, can have multiple charges. The monatomic ions are going to be ones off the periodic table. These are going to be your elements. The other type you can have is polyatomic, and this is where you have an ion that's made up of more than one atom. There's a whole chart of them on the back of your periodic table. Now, to write the formula, as I mentioned before, the cation is written first, the anion is written second. And the overall charge between all of the ions has to be neutral. So the cation charge should equal the anion charge. And the easiest way to do this is with swap and drop. Okay? So here's how we do this. Here's an example. Determine the formula for the ionic compound between gallium and sulfur. Well, if we look on our periodic table, gallium is +3, sulfur is -2. So what's going to happen here is that, remember me saying we always have the positive first and the negative second. To do swap and drop, we need to get these charges to equal. So we can do it one of two ways. We can think of it as, okay, well, we have a +2 and a -2, or a +3 and -2. Okay, so common multiple is going to be 6. So I need to make this +3 into a positive 6. Well, I know I need 2 of these gallium atoms to make positive 6. Then I go to the sulfur. Okay, well, I need a negative 6 to balance my positive 6. So I have a positive 6 here now. And then I think, okay, well, I'm going to have a negative 6 to balance that out to get to 0. So, okay, I have negative 2, so that means I'm going to have to get 3 of the sulfurs to get a negative 6 charge. Well, if you look here, if we take the 3 and we make it the subscript, ignoring the charge, and we take the 2 and make it the subscript here, which is what we call our swap and drop, then we get Ga2S3. We have a neutral charge. So, swap and drop, you take the numerical value of the charge and make it the subscript for the opposite atom. Now, one thing I will note is if you have polyatomic ions and you have more than one of them, they have to be in parentheses. So one example would be like magnesium nitrate. Magnesium nitrate, magnesium's plus 2, nitrate's minus 1. So you have 1 magnesium, 2 nitrates. But we have to put it in parentheses right here to show that we need more than one of those. Alright, now we can write the formula for ionic compounds. Then we can also take the name. We can also take and name them. So here's how you name them. You always name the cation first. If it's a monatomic ion, you use the element's name. The only thing that changes is if it's a transition metal. The charge has to be written as Roman numerals to distinguish what the charge for that atom is. If it's a polyatomic ion, you just use the name of the polyatomic ion. So you name the cation first, then you name the anion. If it's a monatomic ion off the periodic table, you take the root of the word and then add IDE. So let's take, I don't know, iodine. So we're going to take off the INE, which is ide, and we're going to add IDE. So iodide is what it becomes. And then if it's a polyatomic ion, we just use the name of the polyatomic ion. So here's an example. Name FeF2 and MgNO3 2. Okay. Well, Fe is minus, or excuse me, F is minus 1 because it's in group 17, and there's 2 of them. So then Fe has to be plus 1. You also notice here we can kind of go backwards. There's an understood 1 here, and we can use our reverse swap and drop to figure out what the charges have to be. Okay, so we have Fe plus 2, and that combines with Fe minus 1. So because Fe is a transition metal, we say iron, 2, which is our Roman numeral, that's the charge of iron, fluoride. So we take fluorine, we drop the INE, and add the IDE. Okay, the second one, magnesium is its first element. The second one is nitrate. That's the one that's a polyatomic ion. I looked that up on my polyatomic ion chart. So we put the 2 together, magnesium nitrate. Now, covalent bonds are slightly different than ionic bonds. Covalent bonds are going to be ones that result from sharing of valence electrons versus transferring. Because in the to create ions, you're actually transferring valence electrons. And a molecule is 2 or more atoms that are covalently bonded together. Remember me saying earlier, we're going to use molecule and compounds interchangeably. And typically, these are going to happen between nonmetals or diatomic atoms. This is very important you know what your diatomics are. Okay? Remember, it makes that kind of 7 in the corner of the periodic table, plus you have nitrogen up there. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They're very, very important that you know what these are. And the properties of covalent compounds are that they're typically soft and squishy. They have a lower melting point and boiling point than ionic compounds. They're more flammable. They do not dissolve well in water, and because of that, they have a low conductivity. Alright, how do you name covalent compounds? The main thing is you need to know your prefixes. Okay, this is written on your naming flowchart. A lot of these prefixes you know from before. So, you name your first element first. Okay, you're given 2. Typically, you're given 2 nonmetals. You use the entire element name, and you add the appropriate number of prefixes based on how many of you have. The only one you don't do is if there's only one of them, you do not put mono. The convention is just to name the element instead of, if there's only one of them, just use the name of the element. The second element, then you name, and you follow the same rules kind of with ionic. You take the root of the word, you add IDE. So again, if we had iodine, it would be iodide. And then again, you apply the appropriate prefix. This time, if you only have one, you do say mono. So we could say monoiodide. Okay. So name SO2. Well, S is sulfur. So there's one of them. We just write sulfur. Oxygen. Okay. So we're going to take off that part, and it becomes oxide. Alrighty. And then we have two of them. So we add di. So it's sulfur dioxide. This one's actually pretty straightforward. Alright, along those same lines, we can also talk about naming acids. And we really have two types of acids. The first is a compound, an acid that has basically an element off the periodic table. It doesn't have a polyatomic ion. So in this case, it'd be like HCl. Okay? So we take the root of the one word. Okay, this is all based off of the element, because with these we ignore the H. We ignore basically that the H exists. It's just there to tell us that it's an acid. Okay, so we take chlor, which is the root of chlorine. We're going to add hydro in front of it, hydrochlor, ic at the end, and we're going to stick on acid. So chlor is our root word. We put hydro in the beginning, ic on the end, and then we add acid. Now, this is only with elements. Okay? Not polyatomic ions, only with elements is when you use hydro. Okay? A lot of y'all were wanting to use that when it was a polyatomic ion. Now, with a polyatomic ion, you use the root of the word. So if we're doing nitrate, let's say, we're going to take nitric, we're going to take okay? So we take NIR, it ends in ATE. So we're going to change the ending to ic. So it's nitric acid. So we add acid. If it was nitrite, okay, again, we take and this time we're going to add nitrous acid. Alrighty, so let's look at an example. Name HI and H2SO3. Okay, so iodine is off the periodic table, so we put hydro there. Hydro, iodic acid. Hydroiodic acid. Then this here is not being able to. Alright, so this one here, okay, this is sulfite. Okay, for some reason with sul, it becomes sulfur. Okay, and then you add, because it ends in ite, you add us, so it becomes sulfurous acid. So for sulfate and sulfite, you use sulfur, and for phosphor, you use phosphor for phosphate and phosphite. Not quite sure why they go back to that, but those are two of kind of the exceptions. Alright, so one of the things we can talk about now is we can talk about covalent bonds. And with covalent bonds, you're sharing the electrons, and we can use the fact that these electrons are being shared to kind of talk about what the range of the electrons are. And we have something known as a Lewis structure. Okay? And this is what will show us how electrons are arranged. But to start with, we have what we call electron dot structures. And electron dot structures are going to be structures that will show you the arrangement of the valence electrons for an atom. So, if we were doing nitrogen, nitrogen has 5 valence electrons. We would do 5 dots around nitrogen. and this would be the electron dot structure. But it doesn't really tell you a whole lot except for about nitrogen. So what we are more focused on in this class is going to be we call the Lewis structures. And Lewis structures is not just for a single atom, but for an entire molecule. So it takes all of the electrons into account and how those electrons are shared within the molecule. And each atom in a molecule should abide by what we call the octet rule. And this says that basically everything wants 8 valence electrons. Now, the only thing that's special about this is hydrogen and helium, because of where they are, only need 2 electrons to be happy. So hydrogen and helium only need 2 electrons to be happy. So how do we go about figuring out how to draw a Lewis structure? Well, the first thing you need to do is you need to figure out the total number of valence electrons for a particular compound. So all you're going to do is you're going to look at your periodic table and count straight across, ignoring the transition metals, and that will give you the number of valence electrons. So if we had our little periodic table here, okay. Wow, I made the transition metals really big. Okay, so group 1 has 1, group 2 has 2. We're going to skip these guys. Group 13 has 3, group 14 has 4, group 15 has 5, group 16 has 7, group 17 has 7, group 18 has 8. So you just count straight across, skipping the transition metals in the middle there, and that will give us the number of valence electrons. So the first thing you do is calculate the total number of valence electrons. Then you draw the first element in the formula in the center. If it's not the first element, it's going to be the one that's by itself, the one that you only have 1 of. And you place the remaining electrons around it. You then draw a single bond to each element to the central atom. And for each bond you use, you're going to subtract 2 electrons because there's 2 electrons in each bond. And you're basically going to keep a running tally of how many electrons you have to work with. So think of it as if you're having a building, you're building a Lego building, and you figure out how many pieces you need, and now you're going to assemble it piece by piece. So you need to keep track of which pieces you've used and how many of them you've used. So once you get all the bonds, you then are going to fill the octet of the surrounding elements. So the ones on the outside, you're going to make sure they have 8. Any electrons you use, you're going to completely, you're going to subtract from the total. And you're either going to do one of 2 things. You're going to place any remaining electrons around the central atom to make it happy. Or if you've run out of electrons, you can't add more electrons, you're going to either create a double or a triple bond to make sure that all the elements have a complete octet. Okay? Now, what happens if you have a charge? This only affects the total number of valence electrons. If you have a positive charge, you lose electrons, like we've talked about before. So you actually subtract electrons from your total. If you have a negative charge, you gain electrons, so you gain that many valence electrons. So you add to them. And you follow the same rules that I just mentioned, just changing your total based on how many, based on the charge. And you should always end up with an even number of valence electrons, otherwise you've done some math wrong. Because we don't have any any odd number of valence electrons. Of course, like anything in chemistry, there are always exceptions, and the main exceptions you need to worry about are going to be the ones that can have less than 8. Boron and beryllium can have a full octet, but they can have less. They can typically have about 6, but they will have less. There are some that can hold more, like phosphorus, sulfur, some of the noble gases like xenon or krypton, or others. Basically, the ones that can hold more, if you run out of electrons, or if you have extra electrons, just stick them around the central atom. That's kind of my rule. the ones that you really need to worry about are boron and beryllium, that they can have less. Alright, so let's draw some Lewis structures. So let's do the first one. We're going to do Cl3 first. Okay, so let's look at our periodic table, and we're going to see that for P, we have 5 valence electrons, and then we're going to have 3 atoms of chlorine, so that's going to give us a total of 7 valence electrons for each one. So that's 21 plus 5 is 26 valence electrons total. So we know that we have 26 valence electrons to work with. So we're going to put P in the middle, we're going to put chlorine on either side of it. Okay, then we're going to draw our single bonds. So we're going to use 3 single bonds, which is a total of 6. So we're going to subtract 6 from here, and that leaves us with 20 electrons. Well, the special thing about this bond is that it counts for 2 valence electrons, or excuse me, 2 electrons when we're counting chlorine and 2 for phosphorus. So we only need to put 6 more electrons around each chlorine to make it happy. So that's what I'm going to do. Alright, so now I use 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. That leaves me with 2 extra electrons. I'm going to stick that around the central atom. So we now want to check with phosphorus, make sure that it has 8. So 2, 4, 6, and then the 2 on top is 8. So let's check our work. Yes, that looks identical to what I have down here in the lower left. So we've done our work correctly. Alright, now let's move on to NH4 plus 1. Okay, so let's look at our periodic table again. We have 5 valence electrons for nitrogen. We have 4 hydrogens, which each have 1 apiece. And then we're going to actually not add 1, we're actually going to subtract 1 because we have a positive 1 charge. So we're going to subtract 1 here, and that is going to give us a total of 8 electrons. Alright, so we're going to put nitrogen in the middle, we're going to put hydrogen around the nitrogen. We're then going to connect everything with single bonds. We have 2, 4, 6, 8. Well, there we go. We've used all 8 of our electrons right now. Well, hydrogen only used 2, so it's fine with a bond. 2, 4, 6, 8. Nitrogen is fine. And the last little bit is that if it does have a charge, we tend to put the whole thing in brackets and put the charge up in the upper corner. So, let's double check and make sure we did it correctly. Yep, our structure looks exactly like the answer there. Alright, last one we're going to do is CS2. Well, C has 4 bonds, and then we have 2 sulfurs with 6 each. So that's, let's see, 12 plus 4 is 16 electrons. Alright, so we're going to put C in the middle, and then we're going to put S on each side. We're going to draw a single bond, and that gives us 4 electrons that we've used. So it's going to leave us 12. Okay, so we need 6 electrons on each sulfur to make it happy, because it has 2 already with that bond. And there we go, we've used up all our electrons. Now, the only downside is carbon only has 4 electrons. So here's where making a double or triple bond is going to come into play. I'm going to erase 1 pair of electrons there, and I'm going to draw a double bond. So we still have the same number of electrons, but now carbon has 6 electrons. So I'm going to do the same thing to the other side too. So then we're going to have 2 double bonds. So 2, 4, 6, 8, 10, 12, 14, 16. We have all our electrons, but then 2, 4, 6, 8. Sulfur's happy there, 2, 4, 6, 8. Carbon's happy now, 2, 4, 6, 8, and that sulfur's happy. So let's double check and make sure our work is complete. Yes, that looks like the one we have. So when you run out of electrons like this, you basically move them from the outside atoms and make double or triple bonds. Alright, so based on what electronegativity the atoms have in a bond, we can actually kind of predict what the bond type is going to be. because bonds are not going to be completely ionic or covalent. You're going to have some sort of hybrid sometimes, or mixture, because it depends on the attraction of the electrons within the bond. And like I mentioned, the electronegativity is the way that you determine it. We actually have three types of bonds. We have an ionic bond, we have a polar covalent, where you have a covalent bond but it's unequal sharing of those electrons within the bond, and then non-polar covalent, which is where you get sharing electrons, equal sharing of electrons within a bond. And based on the difference in electronegativity, you can tell typically what type of bond it's going to be. If you have greater than 1.7, it's going to be ionic. If you have 0.4 to 1.7, you're going to have a polar covalent. If it's less than 0.4, then it's going to be non-polar covalent. So on your midterm, you will see this electronegativity chart. And so let's look up here at what we have. You always want to look for the positive difference. So we're going to look at two different bonds, a hydrogen-sulfur bond and a sodium-sulfur bond. So we look, hydrogen is 2.2, sulfur is 2.58, so we subtract to get a positive. And when you subtract the two, you end up with a 0.38 difference, so that puts you in the range of a non-polar covalent. If you look at sodium sulfur, you're going to have sulfur's 2.58. Sodium's only 0.93, so that's going to create a difference here of 1.67 or 65, excuse me. So since that's so close, we're going to call it polar covalent, but you could argue that it's ionic. But it's right there on the borderline between the two. So again, you can use the difference, and using the values in the table from the previous slide, you can tell what the electronegativity is. Or you tell me, predict the type of bond, excuse me. Alrighty. And the electronegativity not only tells you what type of bond it is, but it also can tell you about the polarity. Covalent compounds are going to be considered either polar or non-polar based on their bond character. And a polar bond is going to have dipoles, meaning you're going to have a slight difference in electronegativity, and you're going to use an arrow to represent that. Okay? So difference in electronegativity does come into play here. So if we were to look at this previous one, we look at, I don't know, hydrogen and fluorine. Fluorine's going to be the most electronegative. So we're going to draw an arrow pointing towards fluorine because fluorine is the more electronegative. Okay, so fluorine here is more electronegative. So we point the arrow, the point of the arrow is going to be, the head is going to be towards the negative end of the bond. Okay? And based on the sum of all the bond polarities, you can determine what the overall polarity of the molecule is. Okay, so if we go back and we look here, we're going to compare phosphorus and chlorine. Well, chlorine's going to be more electronegative. So if we look at our PCl3, which we drew the structure for earlier, we're going to draw arrows that go out away from the phosphorus. Well, here's the deal. Because it's all of the same element, the two here on top are actually going to cancel out because they're the same amount, but they're in opposite directions. However, we are going to have one that's still pointing down, so PCl3 is considered polar because it has a bond dipole still remaining. Now, let's look at silicone tetrafluoride. In this case, fluorine is going to be more electronegative than silicone. So I'm going to draw my bond dipoles all pointing out towards the fluorine. Okay, here's the deal. Again, it's the same element, so the ones pointing up and down are going to cancel. The ones pointing left and right are going to cancel because it's the same magnitude, just opposite directions. So now in this case, because we have no bond dipoles left, we're going to consider this nonpolar. It really all comes down to whether or not you can cancel out the bond dipoles, and if you don't have anything left, it's considered nonpolar. If there's no bond dipoles, so no dipoles, and it's polar if you have dipoles. Okay, that's it for this video.